Hello. I hope you can hear me all right. So, good evening, everybody. Uh, I will just start sharing my screen. All right. Good evening, everybody. So, welcome to the sixth live session of the NPTEL course, Essentials of Data Science with R Software, where we are discussing probability and statistical inference. So, um, I in case some of you have joined this session for the first time, I'm Pallavi Gupta and I'm taking the Friday sessions, 6 to 8 p.m. on Zoom. There are two other sessions happening each week on Saturdays and Tuesdays. The ones on Saturday are 3 to 5 p.m. and on Tuesdays it's 6 to 8 p.m. So just housekeeping notes. These sessions are being recorded and they are being uploaded to YouTube right after the session. Any material that's being discussed in these sessions is also being uploaded to Google Drive, and you have access to all of these links. And these links are given to you in the NPTEL course page, the last thing where it says problem solving sessions. If you click it, you'll be redirected to a Google Sheet where all these links are given. All right. So for these Friday sessions, or I think for all sessions actually, 5 weeks, 5 sessions have been conducted. So today we are at like the halfway mark for this 12-week course, right? And as always, we'll be discussing and solving some questions from this week, okay? And then we'll be going on to the assignments of the previous week. So we were not able to discuss week 4 and week 5, both assignments, the last time. So we will primarily focus on week 5, but if there are any questions from week 4 also that you think we should discuss, we will discuss those, okay? Although I think it's a different group of people who have joined this time. Some of you were there the last time, but some of you were not. All right, so just let me know in case you would like anything else to be discussed. All right, or if before joining, like before we start today's session, if there's anything else that you would like to mention, just let me know. Anything at all? And again, these sessions are supposed to be interactive, so please feel free to unmute yourselves to ask questions, and if not, definitely use the chat box. All right.
Okay.
Yes. Hello. Anything? Yeah. All right. Okay. Cool. Thanks. So let's start this week's discussion. So primarily there were so as to say 4 distributions that were talked about in this week. One was the Bernoulli distribution. One which follows up from that is the binomial distribution. Then we have the Poinsot distribution, and finally the geometric distribution, right? So these 4 cases, and corresponding to each of those, there were functions in R that were also discussed, which are um, week 3, question 5. Okay, fine. So towards the end of the session, we'll go on to week 3, question 5. Just remind me in case it gets lost, but we'll go there. Yeah. Okay. So what I'm going to do is we will quickly take a look at the 4 distributions here on the PPT, and then we'll go on to these R codes. So that's pretty much what is there for this week's discussion. Because also I did not prepare any practice questions for this week, because most of the questions that you see in your assignment for this week, they can be solved when you use an appropriate R code for them, right? So when we'll be we'll be discussing these things in R itself. That's going to be a good enough practice for what needs to be solved, how it needs to be solved. Okay. So I think that should give you a good idea of how to go about it, although it was obviously extensively discussed in the videos, but we will go through all of that again. And yeah, okay, fine. So starting with the Bernoulli trials or the Bernoulli's experiment. So as the name suggests, it's a single outcome option. So, and you're only doing this once, and you get there are just two possible options. And these two options generally, when you have two options, it's generally attributed as success and failure. And it's up to you what you define as success or failure, right? Whatever outcome you are interested in, even if it's sort of loss of something or failure of something, if that's your outcome of interest, you would assign it as success, and the other ones it becomes failure. It doesn't matter if success is a higher probability than failure, right? And these two outcomes, they are mutually exclusive. And so if you remember, exclusivity means there's no overlap between them, right? So when you're drawing a Venn diagram, there's these two circles, they will never overlap with each other. Okay. If one happens, the other cannot happen. It's not going to happen, right? And exhaustive means that no third option is possible. It's just option A and option B, and that is it. That's the sample space. Okay. So typically the probability of success is attributed as P. That of failure will become 1 minus P because total probability has to be 1, and these are the only two options. And so that's the PMF, right? Probability mass function. And because it's a discrete variable, discrete random variable, so you use probability mass function and the corresponding CDF for that. So anything less than 0 obviously cannot happen. Anything more than 1, it means all the probability has been achieved until that value. And anything between 0 and 1 would give you a probability of... So how do you define this thing? So you know that at a particular value of X, the probability is going to be P, right? And at that value, how do you define when you're doing this, uh, when you're doing the CDF, typically what you do is you subtract these two values, right? So 1 minus 1 minus P, that gives you plus P. So that's how you know that whatever the value of X is, it's going to give you P as the outcome. So that is how CDF... That's how you can check that what the CDF is defined is actually correct. It's not being derived. We're not going into its derivation at the moment, right? But we will see something. So now from EF, now if you want to calculate for any distribution, you would be interested in calculating its mean and variance. So this bit was not discussed in the lectures, but can you sort of think how might we proceed to calculate the expectation and the variance? Any idea? What formula are we going to use? Anybody? Would you like to give it a try? Okay.
Question again, please.
Sorry, say that again.
Question again, please.
Okay. The question is, so these two values, the expectation of X and the variance of X, if like can you derive how these values are going to be there? Like in case you forget, do you think you'll be able to derive these? Okay. So
Using what is that? You can get the CMF by... Is it discrete or continuous?
this is discrete, right? You see here, um, right?
Yeah,
There are
yeah.
only two options available, even though
Okay.
it's defined, but 0 indicates failure and 1 indicates success. So
Cumulative function. Yeah.
yeah, so for expectation, now remember how, let's say when you're asked what is the value of expectation of if you're rolling a dice, how will you get the expectation value of what face comes up,
My XPA.
right? So what you do is you multiply each probability of each face of the dice into that value, right? Um, right? So in this case, the only two values that it can take is 0 and 1, right? Typically, failure means 0, success means 1. So these are the only two options. So what you are going to do here is, so this becomes value 0, this becomes 1, and at each of these points, you would like to calculate the probability. So if you remember from the CDF, how do you calculate the PMF? You subtract, like at 0, at these inflection points or at these points where changes are happening, you subtract from the higher part, you subtract the lower part. So it becomes 1 minus p minus 1 at 0. And then at 1, you will subtract 1 minus 1 minus p, which is this. If you solve it, you're going to get p as the expectation. Right? Likewise, you can calculate for x square also. So just instead of 0, you're going to use 0 square, and instead of 1, you're going to use 1 square. The inside probability stay the same. When you calculate it, that also comes up to p. And you remember the formula for variance is E expectation of x square minus the square of expectation of x. So you subtract p minus p square, and you can just rearrange it like this. Right? Does this make sense?
Right, ma'am.
Yeah? Okay, cool.
Yes, ma'am.
Okay, great. Now, can you just tell me, if I have these two values, which of these is going to be greater and which of these is going to be smaller, and why? Or
Variance will be smaller
okay, that's correct. And why?
because p subtracted from p square is subtracted from p. Variance.
Yeah. Good. Yeah. Perfect. Okay. Right. Okay. So this is just a very minor thing, but yeah, that's the right answer. Okay. So now, if that Bernoulli trial, if there were multiple trials like that, they were done, and now you are interested in how many successes were there out of those. You're not interested in what order they occurred, whether it was the first few or the last few or everything in the middle. It does not matter how many successes, but number of successes. So N trials are conducted, N experiments are conducted, and you're interested in K successes, then that sort of a distribution, that the PMF of that variable is going to follow what is called a binomial distribution. And as you can understand, the only parameters they are going to be relevant are going to be N and K. How many trials are you doing and how many successes are you interested in? And the last is obviously going to be P, that probability that you're looking at, right? The probability of success. And so basically now you don't exactly need to remember this formula because you can intuitively guess it. So there are N chances. You are interested in K of them. They can occur in any order. So ordering is not important. They just need to occur. So you'll be doing a combination rather than a permutation. And for each of these, the probability of that success happening is P for those K times. And alongside, for the rest of those N minus K trials, the success is not happening. So it's a failure. So that's 1 minus P times N minus K. This is how you're deriving this formula, right? So it's really simple to derive it, or rather you can, just write it on your own. So even if you forget, it's okay. On the other hand, the expectation and variance of this distribution is a little complicated to derive. So we will not be going into it. Obviously, it's available online. You can go through it, but it's tough. And it's a little bit too much integration things involved. So we are not going there, but again, simple to remember. You are doing the Bernoulli experiment n times. So if you just multiply the expectation and variance you got from the previous example, like for the Bernoulli trial, you just multiply n to both of them. Okay, so that's what you get. And here it's just like a representative plot that I just copied from the internet. Sorry for the low quality. I did not get a more explanatory figure. But you can see here for different values of P and different values of N, how the graph is changing. So if you compare the blue and red ones, so this one on the extreme left and the one on the extreme right, so both of them have the same value of probability. the probability of success, that's 0.5 for both of them. But you can see that n is changing, right? So for that, because of that, here you can see you expect to see that half the successes are going to be the most probable, right? The probability of success is 0.5, which is 50%. So when you do a trial 20 times, you get the output, you get the success on an average 10 times. When you do it 40 times, the outcome returns as 20. And that's what this NP is doing, right? The expectation. N into P, right? So 20 into 0.5 or 40 into 0.5, that's your expectation. And that's where the peak has the highest, like the curve has the highest peak, right? On the other hand, of course, when P is shifted, it's 0.7, but N is 20. So that's somewhere going to be somewhere around 14, which is here, right? So you can understand how the graph is shifting left and right based on what is the value of P and N. All right. Okay. So that's the second distribution that was discussed. And then we come on to the Poisson distribution. Okay. And by the way, Bernoulli distribution, the way there's like a notation for it. So here the random variable x, it's always capital X, and the tilde symbol. And on your keyboards, if you want to find the symbol, it's going to be towards the left of 1 on the keyboard, on the extreme top left. Shift and the number next to 1 gives you this symbol, tilde. And so the way you denote it is the first letter of that distribution. So in this case, that's B. And in bracket, you write what parameters is it based on, right? So it's N and P. And K is obviously something that you are interested in. So K is not defined, like the distribution exactly is not um, defined based on K. It's defined based on N and P, right? As you can see here. And then whatever is K, that is going to be your output in a way, right? All right. So that's binomial distribution. And now for Poisson distribution, there's just one parameter, which is lambda. So the distribution here, you can see again how it looks. Depending on what the value of lambda is, this one shifts. So the smaller the lambda, the more shifted towards the left and a more higher peak it's going to have. The one you can see here in the yellow line. And the higher the value of lambda is, the more shifted it gets towards the right and bottom. Okay. Again, this is just to give you an idea of how it is. So the formula is lambda to the power k, and exponent so e to the power minus lambda and divided by k factorial. And lambda is always going to be greater than 0. It may be a fractional value, so like 0.5, but lambda um, can never be negative. And of course, probability can also be negative, can also never be negative, right? So this sort of a plot is always going to be on the first quadrant, never any of the other quadrants. So generally, the Poisson distribution is your random variable is going to follow a Poisson distribution when the number of trials are very big, but the probability of success of each of these trials is very low. Like, so in case where we were talking about probabilities right now for binomial distribution, we were generally talking in terms of 0.5, 0.4, 0.7, 0.3, things like that. But when it's really low, maybe less than 0.1, 0.05, something like that. In those cases where, so it's like this. For a binomial distribution, when n is really large and the probability is really low, then that lambda and this n and p, they can be compared by this formula, right? So whether you use lambda or whether you use np, it doesn't matter. It's either of them. So either of them should give you the same value. So, but typically you won't have all three of them available for a distribution. And for this one, the expectation and the variance are both equal to lambda. And you can also sort of see this from here. So the smaller the lambda, the more shifted towards the left. So that becomes your mean, right? So you can see the mean of the yellow curve here, it's very close to 0. So it's 0.5. The mean of this dark blue curve here, it's close to 4, or it's close to 5 or 6. And so the lambda is 6 actually here. Likewise, the variance also, the higher the value of lambda, the more spread out the graph is. So the variance is also higher. So this makes sense, right? You can see this visually here. Okay, that's points or distribution. Now, there are two sort of additional concepts which are just worth keeping in mind when you're talking about the Poisson distribution is that, let's say there are two random variables, and if there's a third random variable, which is the sum of these first two random variables, and if these two random variables are following Poisson distribution, then that third one, which is the sum, is also going to follow Poisson distribution, where now your new lambda is going to be the sum of the previous two lambdas. So that's additivity. And the next one is, so here we are defining the distribution with how many successes are happening. So k successes are happening. Right? So now, if k successes have this formula, then k plus one success, of course, you can solve it again, but there's a simple additional, like a simple mathematical rearrangement that can be done. So what you can do, that k plus 1 is going to be lambda upon k plus 1 times your probability of when k successes, right? So this thing, if you multiply, let me draw a better circle. So yeah, so if this thing you multiply with this thing, then you get a new value, right? So, and it's applicable to any k. 1:2, like from 1 you go to 2, from 2 you go to 3, or from 100 you go to 101. Okay. Now the last distribution that is there for that was discussed this week was geometric distribution. So if you remember, for binomial distribution, what we said, that there were n Bernoulli trials, there are k successes, and you're not interested in the order of those successes. This one's slightly different. Multiple Bernoulli experiments are done, and now what is happening is that the first success that you got was in the kth trial. So until k minus 1th trial, so let's say let's say I'm defining k as 10. So it means in the first 9 trials, k minus 1, right? In the first 9 trials, it was failures. And then in the kth trial, you got success, and you're not interested in how many you do ahead of that, right? There is no n here. You did multiple experiments and you did experiments until you got success, something like that. Okay, so you're not interested in what's happening after you got success. So again, it's relatively simple to derive these formulas, right? Yeah. So the way you can do it is, so there's no combination here. For 1 to 9, there were failures, and on the 10th, success. So again, you have the same probabilities. For success, it's P. For failure, it's 1 minus P. Um, so what it means is that for the first 9 trials, or first k minus 1 trials, it was failure. So 1 minus P to the power k minus 1. And on the kth trial, you have the success. So this one's pretty simple, right? This one, it's not very intuitive, but try to go with me. So now you're interested in successes at the kth turn or anything after k, right? So what you want is that you should have at least k minus 1 failures. That's your minimum requirement. Anything beyond that is sort of something you're not interested in. It can happen anytime, whether it happens on just the kth chance, or k plus 1th chance, or k plus 2th chance. You're not interested, right? So k minus 1 failures. So that's what we have written here. Okay. It's not very, very intuitive, but that's how it works. Okay. And again, deriving the expectation and the variance is not very straightforward. So I would like the only thing I can recommend you to do is remember it, right? So that's the value of expectation, 1 minus P minus 1. And this is expectation multiplied by 1 minus P. Now, again, just like we discussed for Bernoulli's or binomial, where variance is going to be smaller. In this case, variance is actually going to be
Can you
larger.
make
Sorry.
hello?
Yeah.
Ma'am, can you explain that P of X greater or equal to K
K.
equal
Yeah.
to, yeah, K?
The greater than K, right? X greater than K.
Yes, ma'am.
Okay, let me just draw something out. Okay. So let's say if I have, okay. So what I am saying here is that, so let's say I'm defining K as 5. Okay. So what I mean when I write X needs to be greater than equal to K, which means X needs to be greater than equal to 5, it means X can be 5, it can be 6, it can be 7, it can be any value. I am not interested in when it happens, but it should not happen before 5. This is what the statement means. 5 or after. So not until 4, right? So not until 4, which means not until k minus 1, which means you're going to have failures, all failures until k minus 1. With me till here? Yeah, this part is okay, right?
That part okay, but how it is equal to 1 minus K,
Yeah,
1
yeah, yeah,
minus
yeah.
K
I'm
also?
I'm telling you. So is this bit okay? Like
Oh, yeah,
this
that is
this
okay.
bit is okay, right? So you're gonna get failures until k minus 1. So let's say here a failure, 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 right? This is the fifth chance. So we are not interested in what is happening beyond the fourth chance, but the first four chances have to be failure. So the probability of failures is 1 minus p to the power 4. This thing happening is 1 minus p to the power k minus 1. So that's what this thing is.
We want the outcome after K and K plus
So
1.
we are saying success should be after, should be at or after k, which automatically translate that should be failures until k minus 1. So that's what we are doing here. It's just rearranging the statement. It still means the same thing, right? So this is greater than equal to k. It's not only k. We are not interested when the probability is happening, when the success is happening. It may happen on the fifth chance, like the kth chance, or k plus 1 chance, or k plus 2 chance, or k plus 100 chance. But what we want is that it should not happen before k. Before k, it should all be failures. Convinced? Not convinced?
Yeah.
Okay. I really don't know any better way to explain this. Because see, the random
Actually,
way, say
after
that again.
probability, we have to add all the things, no? P of
Yes, yes, I
X equal to
understand.
K.
I understand. I understand. Uh, but the main difference there is in the actual probability, you know what the total number of turns are. Here, we don't have an upper limit to it,
Yeah.
right?
No, no upper limit.
No upper limit. But still, the total probability should always be 1.
Yeah, yeah, total probability 1 minus P
Well,
of X
yes,
less
that is true.
K.
1 minus something is more intuitive. I understand. I completely understand. But the way geometric progression works is that you only have information until the first success. You don't have information after that. So you have information
No,
about all the
after K,
failures
we don't
and
know
that
information.
success.
After K, we don't know information, you are telling.
No, yes, that's right. And k here can take any value. So what we have with us is before k. We know that before k is going to be all
Yes,
failures.
we can include the probability that X equal to K also, no? So we don't have probability for after K, it is 0. Or we don't know means,
So we don't know what k is, right? K could be anything.
yeah.
I mean, see, in a way, you are only doing k turns, k trials,
Yeah.
right? So yeah, the thing is that k can take any value. There are as many turns. Um, maybe I can recommend you something. I have also not tried this, but just to be convinced, you can try taking some value. But again, I don't know if this sort of a thing can be derived, but like you can take a few different values of k. Um, like let's say there are going to be 10 turns. What is the probability that x is going to be greater than 6? So where k is 6. Now you solve it the way you're thinking, where it's like total minus up to there.
We don't
Um,
have the probability after 6, x equal to 6.
yeah,
How
yeah,
to
yeah,
calculate, you're telling?
yeah. Um, okay, let me reframe. So here we are saying the success. So x is basically successes, right? The random
Yeah,
variable which is taking values of success. So success should happen at or after the kth chance. Now it can
yeah.
happen. Now k can take any value. That is true. But you also end your trial whenever k is reached. Whenever n is equal to k, that's where the trial ends.
Okay,
Okay, what I can do is I will try to have a graphical representation of this thing in the next class. Or if I'm
okay.
able to do it before that, I will put it on the discussion forum because I sort of have it halfway in my head, but I'm not able to frame it right now. But that's a very good point you raised.
Yeah,
So for geometric distribution, maybe something graphical for p x greater than equal to k. Okay, I'll keep this in mind. Yeah,
okay.
but yeah, for now, this is the workflow why you reach this formula that after k and later you have successes, which means before k it was all failures. So failure probability is for one failure, the probability is 1 minus p, and for all failures, you have that to the power 4 or that to the power k minus 1. Okay.
Yes.
All right. And these are the formulas for expectation variance. The only thing, the best way to go about it is to remember it. Also, there's something called lack of memory, which is associated with the geometric distribution. So what it means is,
Ma'am, throw some light on x equals to k part also.
this one.
Yes, yes.
Okay, sure. So just like we drew this one. So for this thing, so what we are doing is, again, how are we defining geometric distribution? We are saying so each trial is a Bernoulli trial, wherein you can have success and failure. But what you're doing is here, instead of that binomial thing, so in binomial, what was it? You did the experiment n times. You are interested in how many times did you get success? Not interested in which order did you get it in. That was binomial. In geometric, you are running an experiment. Let's say you're tossing a coin, or let's say you're tossing a coin, and you will say that I am defining my success as getting heads, and I will toss the coin until I get a head. As soon as I get a head, I'm going to stop tossing that coin. Now it's probable that you will get heads in the first try. If you do that, it's over there. The next day you do it, you probably get heads in the third trial. So in the first and second trial, you got tails, and then in third chance, you got heads. You ended there. Some other day you do it, you have to do it. Let's say for whatever reasons, for 9 trials, you did not get heads. You got tail, 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 tail 9 times. And in the 10th trial, you're getting heads. So that 10th or that third or that first trial where you're getting your success, whatever you have defined success as, whenever that kth trial is getting the success, that means that was the first time you got success. Uh, First time kth trial must have, it's like k trial has the first success. That means everything before that was failure. Because these are the only two options with you, right? If the first time you got heads was in the 10th trial, that means all other 9 trials before that, they were tails, they were failures. So that's it. So that distribution, it depends on how probable something is, right? if something is very low in probability, right? 0.1, 0.2, then there's a very good chance you'll get a lot of failures for that until then, right? For example, if I ask you, I'm tossing a coin and it's an unbiased coin. So 50-50 chance, right? Do you think if I'm tossing that coin for 9 times straight, I'm gonna get tails? Do you think that's gonna happen? Like, what does your intuition say? I get tails, tails, tail, 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 tail every time. In the 10th chance, finally I get heads. How probable do you think that is?
It may be.
It may be, but see, when you're tossing a coin, you will expect every alternate chance to get a heads. Of course, we know in 1 or 2 or 3 chances it's not possible.
Yes, yes.
But straight away you're getting 9 heads, sorry, 9 tails.
9 tails.
It's very unlikely, right?
Hmm.
But on the other hand, if
But
suppose
occasionally it may be happen.
it may be
But
happening, that is right.
yes,
But most of the time, this does not happen. That
yes,
out of 10
agree.
chances, 9 chances you're getting one thing. On the other hand, if instead of that 50-50 thing, if I had a different coin, which was like a biased coin, one side was heavier than the other. So what ended up happening was that tails can come more often. Tails can come like 80% of the time, maybe, or 75% of the time. So the probability is now shifted to 0.75 and 0.25. 0.25 being my success. So then in that case, this thing happening, until the 9th chance that happening, that's more probable. It's more believable. Yeah, okay. 75% is the chance. So 9 times out of 10 it's happening, it's more probable. So what I'm meaning to say is this is what is the power of this term P, or this P here, and the K. So again, so you have whatever number of trials you're doing. In the first trial, you had failure. So it is going to be with the probability P. In the next trial, also failure. In the next trial, also failure. You keep getting failures until a particular trial where you finally get your success. Right? So think of it.
Hmm.
So it's sort of, you no longer have a permutation. You have a fixed pattern already given to you where the last entry of that pattern is success and everything before that has to be failure.
Okay.
So what is the probability of this thing happening? So again, it's these numbers, right? So 1 minus P, 1 minus P, this is going to be 5 times. And on the kth trial, if this is K, then this is becomes K minus 1, these whole
Hmm.
thing. This
Yes,
is kth, this is K minus 1 times. So
yes.
1 minus P to the power K minus 1 into P.
Hmm.
That's this probability here.
Okay, kth is the final success power,
Yep,
which
yep.
is getting multiplied here.
So
To the,
this thing is one term, right? P
yes,
is
ma'am.
outside, 1 minus P is to the power K minus 1.
And the p, we can also write p to the power k, kth.
So kth. So kth
Kth is the
turn,
success.
kth is the trial at which it is happening, but it's only happening
Mhm.
once. Power
Okay,
means how
okay,
many times it's happening, right?
okay.
So if you remember this one here, so what are we saying here? So again, like this, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say you did 10 trials. So n is equal to 10 in this case. Now you say that success happened thrice. So I'm defining success here, here, and here, let's say. But I can also define success. So let's say these are 10 more chances. It may happen in some other turns. So these three successes can happen in any of the 10 turns, right?
Yes.
So 3 out of 10. And I'm not interested in the order,
Okay.
right? I mean, I'm interested in the order, but as in, like, this is S1. No. Yeah, I mean, um, I'm interested in whether it's these three or whether it's this, and this. But exact order, I'm not interested. It's the combination. Which of the three? First, second, and third is okay. But I'm not interested if it's 1, 2, and 3 or if it's 3, 2, and 1. That doesn't make sense, right? Just which chances it happened out of 10. So how many options are there? This is n choose k combination, right? how many ways of selecting 3 slots in a 10 slot position, right? That's what this indicates.
10 CK, yes.
10 CK.
10
And
C3.
right. And now, so what is the probability of each of these 3 happening? P into P into P, right? So P to the power K. This is what this term is showing.
Okay.
And what is happening in the other remaining 7 slots?
Failure
It
part.
is failure to the power 7, right? So that is
Okay.
N minus K, which is this term. So here there were more than 1 successes, right? K can always be 1 also. Maybe there was just 1 success in all of these 10 chances, right?
Okay.
But in this case, the N choose K term is actually missing because you're not choosing. You know it's happening on the last trial.
Okay.
K is your last trial and it is happening on the kth trial. So there's no power for this P.
Okay.
All right? Okay.
Okay.
Great. Fine. Thanks for asking the question. Okay.
As it is a first trial, the P may be a 1 probability of success.
Yep.
As it is a first trial, P of x greater than or equal to K is the first outcome. No. Geometric.
Geometric, huh?
P of x greater than or equal to K.
Uh-huh.
As it is the first outcome as success.
Hmm.
So is it P equal to 1 probability of success?
If it's happening on the
If it is,
first turn.
yeah, first outcome as is kth trial, no, is a success.
Kth
So
is the
different.
trial itself, right? First chance of kth doesn't make sense. Like then that means K is equal to 1.
Oh,
So again, remember, you are ending the trial as soon as you get success. So I am tossing a coin. I will keep tossing it until I get heads. That's it. Once I get 1 head, over. I'm not interested in what's happening after that.
okay.
On one given experiment. So today I'm doing it, I get it in the 10th chance. Tomorrow I might get it in the 11th chance. So that's what this
So
greater than K is.
so the probability in this case, when K equals to 1, in case of coin, it is 1 by 2 only, because x equals to K equals to 1 here.
Say that again.
Uh, for the same question, the other person is also asking,
Uh-huh.
when K equals to 1 means
Uh-huh.
K here it's also a trial part, no?
Yep,
So
yep, yep. Yep. So
so
K is 1
K
means in the first
uh,
chance you got success.
success
So
means the probability is 1 by 2 in case of coin.
yes. And see, and why that makes sense? You're right. It is 1 by 2. So
Mm,
success in first trial. So it means it is equal to P. You got success.
yes,
And for a coin, it is 1 by 2.
1 by 2.
And you can
Yes,
also, just for sort of like a sanity check, you can check it from this formula also. There were
yes.
no failures. So
Hmm.
K1 minus 1, 0.
Hmm.
Anything to the power 0 is 1. So you got P.
Because I am applying this formula
Huh.
only,
So applying
because we
formula
on
also,
the first trial I am getting the
yep,
success,
yep,
so
yep.
other part is also
So K is 1, makes sense. And you
okay.
can also think about it, like forget
Hmm.
geometric distribution. You got it in the
Yes.
first trial. How? So that's a simple coin toss question, right? What is the probability of getting heads when you toss the coin once? 0.5.
Yes, if we applied this formula also,
Yes,
we
when you're
can
applying this formula also,
mm,
you're getting the same answer.
same answer. Okay.
Perfect. Yeah. Good. So yeah, oftentimes in probability, as we have also seen a few questions in previous weeks, sometimes you have more than one formula or more than one way of doing the same question. So if you think you can solve the question in more than one ways, go for it. And if you get the same answer through both the things, then you're perfectly sure that that's the right answer, right? Okay. So this lack of memory thing that was mentioned, so it was pretty clear from the example. So here, when you're tossing a coin, so let's say if the coin, so I have a coin today, I tossed it 5 times. Tomorrow I'm tossing it again. instead of tomorrow, if I would have started tossing it right after my first 5 trials, would it have mattered? The coin doesn't say, oh, I'm tired, I'm going to give you a different probability today and a different probability tomorrow, right? It does not happen. So whether I say it's 1 to 5 today and 1 to 5 tomorrow, or I say it's 1 to 10 today, it doesn't matter, right? So what happened 1 day ago or what happened 5 trials ago, it does not matter. The probability of getting any success or whatever in trial 6 to 10 is the same as how it was for 1 to 5. It's the length that is more important, right? What is K? If K is 5, so 1 to 5 is of my interest, 6 to 10 is also of the same funda, 50 to 54 is also going to be the same thing, 101 to 105 is also going to be the same thing, right? So that's the
Yes,
lack of
ma'am.
memory bit. That it does not matter what position overall you are interested in, but those 5 trials or the fifth trial, whether it's fifth from first or it's fifth from 100. Okay. All right. So for each of these, we will take a look at some commands in R. So I hope you are sort of familiar with how R is working, right? How R Studio is working. So again, whether you use R or you use R Studio, it's your personal preference. For my work in my PhD, I've been using R Studio more extensively, so I'm a little more comfortable with that, and it's also giving you a little flavor of R from the lectures in R Studio here. So I thought it's worthwhile to discuss it through R Studio. But again, doesn't matter which one you use, it's going to give you the same answers anyway. So we'll start off with the Bernoulli and the binomial distributions. Again, Bernoulli trial is just one trial. So we are mostly interested in the binomial distribution here. Now, of course, so there are 4 formulas for each of these distributions that are being discussed. The first one is giving you the PMF, or the probability mass function, which is D binom. Okay, this thing. The second one that we talk about is P binom, which is giving you a CDF, or the cumulative distribution function. The third one is Q binom, which is giving you quantiles in which the values are distributed. And the last one is R binom, which is a random number generator, which is generating numbers that would follow that sort of a distribution. Okay. So when we talk about the binomial distribution, so we have talked about, if you see here, we've talked about 2 values, N and K. Sorry. Yeah. Uh, N and P. These are the 2 parameters, right? You remember this thing here. So N is how many trials are there, and P is what is the
Probability of
success.
success.
Sorry. Hello. Okay. Yeah.
Probability of
So
success parameters. Probability of success parameters are
yep,
N and
yep,
P.
yep. Perfect. So this is how we are defining a binomial distribution, right? N and P. So size and uh the probability, right? So one of the arguments that you're going to write inside the function, it's going to be the size, right? Which is N in this case. Again, the way things are written in R can be a little different. So there's no N here, but instead there's this parameter, this argument called size. There's no parameter P here, but it's probability. So it's roughly the same thing. And then this value here, the value X that you're giving, this is what values can K take. So now remember, this is a distribution, right? It's a distribution. So what we are interested here is looking at that distribution, right? So again, just to show it to you from here. So P and N, and what you see here on the X-axis is actually K, right? So you can input P, you can input N, but to make this plot, you need the X-axis also, right? The Y-axis is calculated from here, this probability. So it's probability corresponding to different values of k. Okay. When k is 1, what is the probability? When k is 2, what is the probability? When k is 3, what is it? So on and so forth. Until n. K can be a maximum value of n. So that's exactly what we are doing here. So total number is 30. Probability of success is 0.3. And let's say I want to look at the whole range from 1 to 30, or I want to take it from 0 to 30, whatever. So when I run this, so again, what I'm doing is my cursor is here. I'm pressing Control Enter. When I do that, I get 26, 27, 28, 29, 30. I get 30 outcomes. Okay. So this is the probability when, so this right here is the probability when k is 1. This is when k is 2. This is when k is 3. When it's k4, when k is 5, and so on. Okay. Now, if I want to see this thing, I want to make this plot right here. So whenever you want to make a plot, you need the x-axis and you need the y-axis. So the first value you, inside the plot function, the first thing that you write is your x-axis entries. So it has to be a vector, right? So 1:30, that is going to give you a vector. And this outcome here, it's the exact same thing again. You can also save it in a variable and write the name of the variable here. That's up to you. But these become your y values, y-axis. So I'm plotting x versus y, x comma y here. I'll press Control Enter, and you can see here, this is what it looks like, right? So it looks pretty good. It looks very similar to what you saw here, right? So we've successfully plotted the binomial distribution. Okay. Just to note, so when I came across this formula, I got thoroughly confused between x and size here. Okay. So, so again, now ideally k should be within up to, so the minimum value that k can take is 0. The maximum value that k can take is the size, right? So again, this thing I'm plotting the same thing. Instead of 30, now I have 100 here. So when it's like this, you see the trend, right? It's okay. This is how it makes sense. But now in this case, let's say I am interested in a larger value in more Ks. Even though the success is only until 100, let's say if I say, what is the chance that out of 100 trials, I get 500 successes? It's not going to happen, right? It's not going to happen. So it should ideally give me a 0. So it does give me a big 0 throughout the whole range. There are zeros elsewhere also, right? It's not that it's non-zero everywhere. But for the extra bit which does not make sense, obviously it's going to be 0. Right? Now, can you think what might be happening here? So what I'm doing here is I have 500, I'm running the experiment 500 times, and I have 500 trials, and I'm only interested in successes 1 to 100. What do you think is happening here? It might be a very trivial thing, but I don't want you to get confused in what is X and what is size here. So just want to be double sure. What is happening here? Where you have, so there are 500 trials, but you are only interested in 1 success, 2 success, up to 100 successes. Any idea? It's a very trivial thing, by the way. Maybe I've not explained it enough, but yeah. Anybody, would you like to try? Okay. Yeah.
Please repeat the question.
Okay. So there are these two parameters, x and size, in this function. Size is n, prob is probability, p, and x is how many values of k are we taking. it doesn't have to exactly be same as size, right? You can be interested in all chances, all successes up to 100. You can be interested in more successes, which does not make sense. So you get 0, obviously. What does this mean? When you are interested in only a few successes, you are doing the experiment a lot of times. So what do you think the plot function is going to be here? What are we plotting? Okay, maybe what I'll do is I actually want to tell you another thing here. So now you can see what happened here. When you're running an experiment 500 times, and when the probability of success is 0.3, so it's basically 30% of your trials are going to give you success. So 30% of 500, that's roughly 170, 168, 170. So now you can see here, the first 100 trials, it's highly probable up to 80 or 90 trials that you are not going to get anything. It's not going to work. You won't get any success there. Most success is going to be between 100 and 150, right? So all I want to show you here is a large part of this plot is missing. The plot, ideal plot, would be between 0 and 500, but you're only plotting 0 and 100, right? So that's it. That's what I wanted to show here. I hope I did not confuse you.
By seeing that curve, what we conclude, what we predict,
So what
that
we predict,
plotting that, yeah,
yes, yeah. So
that
what,
plotting that, yeah,
so what we are saying here is, so it's a binomial trial where we have done the trial 500 times, right? And the probability of successes is 0.3. So 30% chance. So every third, like 3 out of 10 chances will give you success. So you would expect around 150 successes or 170 successes. That is 30% of 500, right?
yeah,
So yeah, so it's exactly 150 actually, right? So now what is the chance that you get out of 500? What is the chance you get only 20 successes? All other failures. So it's not possible, right? Because your chance of success is not so low. It's quite high. 0.3 is not a very low value. So only getting 20 is highly improbable. Getting 500 out of 500 is also improbable. So that's what these plots are actually telling you. So for this plot, what we did, we had 100 trial and we are seeing what happens, how many successes can you get. So 0 out of 100 success is also highly improbable, that all the time you're getting failures. And 100 out of 100 is also very improbable, that all 100 are going to give you successes. But 30 out of 100 is quite probable, and that is because it's 0.3. That is what the mean is, right? 0.3 into n, p into n, 100 into 0.3, 30. That's the mean. Okay.
Purpose of plotting that probability, that outcome size, what is the purpose of seeing that?
So generally when you're plotting, so when you have data sets, whenever you have a lot of values, it's a nice practice to visualize it. I mean, of course, even if you don't visualize, it's okay. But what we are doing here is just to get an idea of how the plot looks. So this thing is basically your y-axis here. In the plot function, the first argument you write is the x-axis, and this is going to be your y-axis. So your x-axis here is going to be the input for the d-binom function. So for as many, so it's basically whatever values of k you are interested in. So what I'm doing is basically calculating this thing. N and p are fixed. We fixed n at 100. We fixed p at 0.3. For different values of k, you'll get different probabilities, right? This whole thing K can be 1, you'll have some value of probability, K2, some value, K99, some other value, K100, some other value. This is what this also plot is showing. X-axis you have K, Y-axis you have probability. Here also, X-axis you have K, Y-axis is probability. Probability of this K. This X is actually K, right? X is a vector indicating the possible discrete values of successes, which is nothing but K, right? Good. Okay, try to, it's a new concept. It's not very straightforward. It took me a lot of time to understand this also, but try to just see whatever we have discussed today and whatever was there in the lectures. You don't need to go outside of it. Try to sit with this. Try to think about why these values make sense. Why is mean n into p? Why do you have a peak at n into p? It's once it hits you that it's going to become very intuitive. Were you asking something?
Ma'am?
Yes.
Yes. Okay. Understood. To visualize the things, we do the graph.
Mm-hmm. Yep. Yeah. Okay. All right. Fine. Okay. This was so this was like this was a straightforward, a single, let's say coin toss or whatever, a single basic Bernoulli trial. But if you remember, there was this, let me write this here. So let's say you had 3-coin toss, right? Now each coin itself is a Bernoulli trial that we understand, right? But for a 3-coin toss, so you remember, so you can say that there are going to be 8 outcomes, right? 8 outcomes. And maybe the way you can define your success here, success can be number of heads. That's what you're defining your success as. So you can have 0 heads, so all tails, 1 head, 2 head, 3 head. Now, if you solve this, you will get these values. This you remember, right? How out of the 8 options, which of these it classifies. Now, I actually want to find out these probabilities in through R. Okay. So the way you can do this is this is also binomial distribution. Again, probability can be anything. That's up to you. It's if it's a unbiased coin, it's going to be 0.5. If it's a biased coin, whatever. And now size in this case is 8. There are 8 options. There are 8 outcomes. Right? So n is so each of the total sets that we are defining as binomial distribution. Each of those becomes a Bernoulli trial, right? Whether you get success or you don't. But now, how many successes can there be? What is the value of k? It can only be 0 and 3, 0, 1, 2, 3. It cannot be beyond 3. Right? That's how we are defining number of, that's how we have defined the success. Right? Even though you have 8 outcomes, 4 heads does not make sense for those 8 outcomes. Again, this is not very intuitive, but this is how we are doing that. So when you do this, you get these values. Okay, 0, 1, 2, 3. And so just give me a second. Yeah, right. So in fact, if you try to do it, yeah. So anyway, so once you do solve this, here in this case, these values were using considering that they were it was an unbiased coin. But this one, when you have a biased coin with this probability, this is the output that you get. Again, you can plot this. It doesn't exactly look like a binomial plot because we are only looking at the first few things. But these values are still exactly what you would calculate from if you do it manually. All right. So this is the first type of the command which is available, where you are actually calculating the PMF. Corresponding to this is where you calculate the CDF. And again, it's the same thing. You have probability and you have size. Instead of writing X, here you write Q. But it's the same thing. You see, it's the same order, same everything. You calculate this. You can also plot it in the same way. So now, if you can see this thing happening. So what the CDF does is, CDF is ever increasing function. CDF can never be lower at a value than it was before it. It's increasing. It's a monotonic, non-decreasing function, so as to say. It will never decrease. It may increase or it may stay the same. Right? So this is what the CDF for binomial distribution looks like. Again, you can also do it for the coin toss example. Again, that's also increasing. Nothing new.
Ma'am, what does this argument lower dot tails define
Yes,
here?
yes, yes. So, uh, lower dot tail. Uh, 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 uh. Oh, yeah. Let me show it to you. So that I'm not wrong. The binomial. So lower dot tail, when it's true, so by default it's true, it will calculate the probability of up to that value. So this value, this is only there for so you remember for CDF, right? We are talking about up to a certain value. So this is what that up
Okay.
to means. Less than or up or that. Less than or equal to. So that's what CDF normally does. If you're interested in after that value, then you can do it. You can so let's say
Ma'am, if
it,
we put lower dot tail
yeah.
equals to false here,
Yeah.
how does
Yes,
make some
I
difference
am
here?
plotting that. So this one, it becomes the reverse. It's one minus everything. So
Okay, okay.
this plot right here, at every point you do one minus that, one minus that. So here it was roughly 0. So 1 minus 0 is roughly 1. Here it was 1. So 1 minus 1 is 0. So it's the exact
Okay.
1 minus of that plot.
Opposite. Okay.
Because you were interested in up to x, and now you're interested in after x, greater than
X.
x. So thanks for
Okay.
pointing it out. But yeah, when you're doing CDF, so this ideally, as such, is not CDF. Not what you conventionally define CDF is. Right? Because CDF is up to that value.
Okay.
Not right? And conventionally. Yeah. Yeah. Fine. Then again, for quartiles, so again, probability and size. That's how you're defining binomial distribution. And you are interested in what is the value. So again, just so that I'm not framing it wrong. So in this case, this quartile thing, which is okay, also just it's very funny thing. For P binom, the argument is Q, and for Q binom, the argument is P. But that's just how it's named. Okay. So so yeah, so for P binom, Q, that quantile that we're looking at is what's the word I look for? Okay, so So basically what Q binom is doing, it's calculating the value which falls within that quantile. The highest value that falls in that quantile. Okay, everything below is less than 0.6%. So like this. So if I plot this thing again, let's say this one. So now you can see at value 10, if I draw a straight line here at 10, 60% of my values will be below that. So I was interested in the 60 quantile. So at k is equal to 10, below k is 10, 60% of my trials will go into that, right? 60% of the area under the curve. What value divides the curve into 60 and 40? Right? And for the other one, so again, for all of these things, you can calculate. It's once you try, you'll get the hang of it. I'm gonna rush through, like after this example for the other distributions, we might rush through a little bit because we don't want to run out of time today also. Okay, so we were here. So now again, so we generated the PMF, the CDF, and quantiles. So the last one is if you actually want to generate this data, right? So, our binom is there. Again, probability and styles stay the same. Now it's just how many things do you want to, how many numbers do you want, right? So from 1 and 30, between 1 and 30, you can have any values. So that's what it gives you, anything. Now, if you remember this coin toss example, right, this thing. So we know you can only have values between 0 and 3. But that value is, that sort of a restriction is not given by N and P, right? The N and P parameters we were using here, they don't restrict your values. The K restricts your values, that K can only accept 0, 1, 2, 3. Now, in case of R binom, when you're doing that coin toss, if you're using R binom for the coin toss, it will not give you, it's going to give you random values. So in 3 coin toss, you can never have 6 heads or 7 heads or 8 heads. But this is what it's returning, right? So you have to be careful that always doing a random number generation for these kinds of examples is not going to help. You need to see if what you're generating, it's actually making sense for the kind of question that's being asked. Okay. Now, if you ask me what is the solution, I have no idea. I would like to look into it. I only realized this yesterday, so I did not have a lot of time to prepare. If I do come across how can we solve this again, I will let you know. But just a word of caution. For examples like these, R binom is a good thing. But for examples like this, where your success is not throughout the whole range of the number of outcomes, I'm not sure what can be done. Okay, fine. So then, of course, once you have these random numbers generated, let's say we are going to take this good example. For this one, you can calculate mean and variance. So as was pointed out in the lectures, and it's also something you know, when you have very few trials, it's not going to help you. The mean and variance are not going to be ideal. You do it 100 times, you do it 1,000 times, the mean and variance would approach the expected value. So the expected value of mean here is it's 9, right? Variance, I don't remember what it is, but so let's say when you're doing for a larger sample size, you get mean as 8.9, which is very close to 9. Variance is 5.7. I think the variance is something around 6, but not sure. But when you have a smaller sample size, the mean is quite away from 9, and the variance is also quite away from whatever the expected value of variance is. Okay. So variance is P into 1 minus P, right? N into P into 1 minus P. So that's 9 into 0.7. So that's 6.3. So you can see that this variance is way off. This one, not perfect, but it's pretty close. Okay. Are we good till here? Did you understand what the four functions are doing? What parameters stay the same? What are
Yes,
changing?
ma'am.
And how is the output changing? And what you can do with those outputs. Okay. It's a little complicated. These are relatively newer commands, I think, for all of us. So if you can spend some time on this, that'll be good. But otherwise, just get an idea of what each of this can do. Fine. Just like we have R binom, we also have, D, P, Q, and R. We also have each of these. So it's binom for binomial. It's POIS for the Poinsot distribution. And it is geom for the geometric distribution. So it's very similar. The only one of the major difference in binomial and Poisson was instead of n and p, you now have a single parameter that's lambda. And that's what you have here, the whole word lambda. So I would just like to add something here. So let's say, so again, what I'm doing is 300, let's say I'm interested in how many successes there are. So K takes 300, 1, 2, 3, 300. Lambda is 10. So I'm going to get 300 outcomes, 300 probabilities. So what I'm calculating here is this thing. Lambda is fixed. For different values of K, I get different probabilities. Expectation and variance should be lambda, as we'll see later. So now if I want to plot it, I'm doing the same thing. It is D poise. Let's say I am not plotting 300, but let's say I'm plotting just 100. So 100 here, and then 1:100 become my x-axis. For the plot function, so this is x, this is y, and I'm adding a color. I'll tell you why. So I'm adding color red. So I get a lambda, this distribution, right? It looks something like this, right? It's pretty much shifted to the left side. Right? That's there. Now, let's say I want to plot another Poisson distribution on the same plot. Okay? With a different lambda. Now, if what I do here, if I say plot again, so once I plot 10 on a red color, and once I plot lambda 5 on blue colors, if I do this, the previous one has gone, right? It's one plot, it's a different plot. But R can allow you to add multiple plots one after the other on the same plot. So what you do is, first of all, you call a plot with the plot function. So the plot function is doing two things. It is making a plot, which means it's making your x-axis and y-axis and these squares and everything. And it's also making these points. Now for the next plot, what I want to do is I only want to add points. I don't want to make a new plot. So what I'll do is I do the exact same thing inside. X-axis, x values, y values, colors. But instead of calling the plot function, I call the points function. So what this function does, it's only going to add points to this graph. So it's a different lambda. So when I run this, you see, it's a different plot now. It's shifted even more towards 0. When I do the same thing, green, you see, this one, it's shifted even more towards the left. Right? This is how it was. All right. So yeah, so you can see the mean and the variance, they resemble what you would expect, right? Higher variance, higher plot for 10 and like that. Okay. I have not explicitly added the CDF and the quantiles for this because it's exactly the same thing. In case you get stuck somewhere, let me know. Let me know on the discussion forum or in the next session. But as such, it's the same thing. Slightly different thing here. Yeah, no, this one I can leave. Okay, so again, same thing. Let's try with generating random numbers. So again, lambda, and how many random numbers to generate? Let's say I want to generate 150 random numbers. So I generate these numbers, right? Now I want to see if they follow that curve, if they look like this, right? So typically 150 is not enough. So let's say I do this 1500. So what I do is I do table. Do I need to do a table? Just give me a second. I want to confirm something. If I run this, yeah, this is what's going to give me the right thing. Okay. So if you remember the plot we saw initially, right? Peak initially and then plateauing down. So I generated random numbers and I'm seeing. So here also you can see it's the same. It's the same trend, right? It's peaking and then it's decreasing. What I can do is maybe I can increase the x to 100. This did not work. Okay, let's check. 20. That's also not gonna work. Okay, let it be. Yeah, okay. Right, so you can see it's following that trend, right? So that's what it looks like when you're generating random numbers. Okay. Again, you can find the mean and variance. So mean and variance should ideally give you the same value as lambda. So you can see when you have 10 points, even then it's not too bad. But it will get better, of course, when n is even higher. So like when n was 10, the difference from the mean was like from the actual value, which was about 6 and like 0.6 and 0.9. And now the shift is only, 0.16 or 0.7 here and there. So it does get better when you have higher values, higher number of sample, or the sample size is larger, right? So that's the Poisson distribution. And again, same thing for the geometric distribution. Now for the geometric distribution, remember, there's just one parameter, which is k. And of course, p is there, but one note with k. So normally in this definition, the way we defined k was kth trial has the success. But what R does is, it says whatever this value of x it's taking, or k it's taking, this is the number of failures. So if you are interested in k at 5, for R, you're going to call it 4. Are we clear on this thing? So
Yes,
we
ma'am.
know
We have to take the one value less.
one value less, right?
Okay.
So k, normally when you say, when like something, so one of you pointed out, k can be 1. For R, k can be 0. So here we are going to start with 0. All right. So again,
Okay.
same thing. You can calculate values and you can put it on the plot, right? Just a word of caution. Let's say, let's say I would have called this as maybe -1. Maybe I wasn't careful. Maybe I thought k can be 0 and I thought, okay, then this k should be -1. So let's say I do this. So now what you can see here, at -1, I got a value of 0. So geometric value cannot be this negative value, right? K cannot be negative. Like number of failures cannot be negative. So for our case, number of failures, and number of failures cannot be negative, because number of success, like trial in which success happens, cannot be 1, cannot be 0, right? So this one is not correct. Okay. So again, long story short, so the chance in which the trial in which you can have the earliest success is 1. Therefore, the number of trials until the first success can be 0 also. So that's why we are starting with 0, right? Uh, Again, for CDF and quartile and random number generator, it's going to be the same thing. I've just shown it to you again that the probability and mean and variance are going to be closer to that value and not. But again, it's the same thing. Yeah, I was just trying something here. So yeah. So these 4 formulas for each of these distributions, that's um that ends the story here, right? So all right. Okay, so this is what was discussed in week 6 of the session. If everything's good with it, we will go into discussing the assignments. I'll start off with assignment 5 first. Okay. Um, since we don't have a lot of time, I don't think we'll be able to cover all 30 questions from both assignment 4 and 5. So I have a few things that I want to particularly focus on. So I'm going to be, since I want to solve a few questions that are there for integration especially. So I will go into those. If anything's still left, I think we will get chances in the upcoming sessions. If we don't, we can always, like I mentioned, we can always have a session at the end where we can take some time and solve any remaining question. But for now, for assignment 5 last week, so this was a
Ma'am,
question. Yeah.
solve the third one.
Yes, I will solve the third one. Yes, I will go on to that. But I'll just walk you through the others just from the top, right? So again, this was 40 to 60, like this. So this is going to be integration, right? And to calculate mean and variance, we are going to use the formula. Mean is basically expectation of x. And when you want to calculate expectation of anything for something which has this continuous distribution, you're going to be integrating x fx dx and integrate over the whole range. And for expectation is going to be, for variance is going to be expectation of x square. So everywhere you had x, you're going to say x square minus square of expectation of x. Here it's a slightly different formula used. Don't get confused. You can stick by the actual thing. So integration of x fx dx minus integration of x square fx dx, that's going to give you variance. Okay. And I think we had solved a similar question last time also. Instead of x, everywhere you can write 4x. So instead of x, you write 4x. Instead of x square, you will write 16x square. Okay. So
Yes, ma'am. And problem question number 8 also.
okay,
I
okay,
have
okay.
some doubt.
Okay, fine. So this is done. Second one, this is also going to be similar. What I will do, maybe not in the few
Ma'am,
upcoming,
only solve the integration part.
just
We
yeah,
just
yeah. So that's what I'm saying. I won't be able to solve them today itself. It will be a lot. So what I'll do is,
okay.
for that extra session, if we do conduct it, we'll mainly focus on integration. But also in the meantime, I will send all of you through the discussion forum, or I'll ask the TAs of the instructor and the TA to give you a small summary of the main commonly used integration formulas and how to go about it, because there are not going to be a lot of them, maybe 5, 6 basic ones and some examples. So I will not go into this one right now. It's also
Ma'am,
roughly the same thing.
only the integration part, if you solve it, it would be a
Okay,
greater help.
fine.
Because
I understand.
putting the value, it's
I
common.
understand. Uh, I let me solve the third question right now. Right? I will solve the whole thing, like
No,
integration
ma'am,
part.
second one.
Second one also.
Yes.
Okay,
Only the
okay,
integration part.
fine. So let me.
If you solve the only x and the function, it
I
would
see.
be a better help.
Right. Uh, okay. Let me add a few more slides here. Fine. Um, sorry. Give me a moment. Capture this one, right? So fine. I have the notepad in me. So this is 20. So we are doing the expectation thing. So we'll have an integration x exponential minus 20x plus, let's say, whatever this value comes up, 25 to 50 dx. Okay.
Yes, ma'am.
So now, um,
Eyelet
20.
function we use.
Say that again.
Eyelet function.
Highlight function. What's that?
8 e power 50 outside, ma'am.
Sorry, I cannot hear you. Say that again.
E power 250 outside.
Yes, that's yeah. So when you have expectation, sorry, not expectation, exponent. So exponent is just another way of writing this thing, e to the power minus 20 x plus 250. So whenever this thing happens, you can write it as, it's not just limited to e, but any exponent, this thing multiplied by e to the power 250. So this addition is basically splitting these two separately,
Yes,
right?
ma'am, got it.
So now so e has this fixed value, right? It has a fixed value. So e to the power 250 is actually a fixed value. It's a constant. So it can come outside the exponent. So along with 20, it can come e to the power 250. We do this and we have exponent 20x dx. Okay. Now this thing, okay, I'll solve it for this question. It's also applicable to question number 3. I just have it noted with me, so I will use that. Now you see
Formula
here.
integral uv dx equal to uv1 minus u dash v2.
Yep. That's so. Let me just do it a little slowly. So I'm doing integration after like 7 years now, or at least 6 years now. So maybe I'm slower than you, but for the sake of it, let me just solve it slowly. So let's say if we have this of this order, integration u dv is equal to u into v minus integration of v du. Let me know if I go wrong somewhere. So
Better formula integral
Integration.
uv
U inter
uv
U
uv dx.
integ
yeah. Okay, fine. If you know a different formula, that's well and good. I have sort of prepared one thing, so I think it's just going to be a lot of confusion if we try that. You can always add that somewhere in the discussion forum. That's just going to help everybody. So let me walk you through one method. If this works better for you, well and good. Otherwise, whatever is working. As long as you're getting the right answer, it's good.
Yes.
Okay. So now if you compare this thing here, so let's say what I'm going to do is I am going to call this x here as u. Okay. And then the rest of this term, which is exponential minus 20, this thing here, and dx, this becomes dv, right? And as a result of, if this is u, then du is definitely dx, right? X is u, so dx is du. And then if this is dv, then v is nothing but an integration of this whole thing. This is really x, right? Now, expectation of any value. So the second thing that you should remember here is that if you have, okay, I'm probably saying expectation incorrectly. Exponent of, let's say, ax here, the integration of this thing is equal to 1 by a exponent of ax. Right? Now, if you compare here, a is actually 1 by 20. Right? So if you integrate this term, what you're going to get is minus 1 by 20 exponent minus 20x. So now you have these, you have u, v, and du. So now you can solve this. This 20 e to the power 250 stays outside. And instead of this whole thing, what you can write is u into v, which is x minus 1 by 20 exponent minus 20x and minus. Now you integrate this thing again. Okay, same thing. Minus 20 here goes in the denominator. So this thing becomes 1 by 400. And exponent minus 20x, right? So, yeah, this whole thing goes here. Let's just write this separately. So, wait. So you should be able to solve this now. It's right. This is the exponent part, right? Like this is the integration part. You've solved this. Now the second part that you need to do is add up these limits. Integration always has these limits. So here the limit was greater than 12.5. So it's going to be 12.5 until infinity. Right? So it's not very clear here. But when you do this, so you see, this is what you got. This is what you got. And you enter these values, infinity and 12.5. Maybe I should just solve it.
I have done this in this way only, but I am not able to find how in the end of this solution we are taking 1 minus
Okay, okay, okay,
exponential.
okay, okay,
This
okay,
part is not coming.
okay, okay.
So how
Now
will I do
you,
this?
okay. Now, so let me solve it ahead. So now the limits that you're going to add here, the limits are in minus, this is 12.5 in infinity, right? So typically you do it like this. Now I would like to show you this term here. So let's say I write minus x by 20 exponent minus 20x. Okay, now let's say I add the limit infinite here. So what is this term? X by 20 into, so negative power always means you do a 1 by. So this is e to the power 20x. Okay. Now this, so this is x somewhere in the numerator. There is an x in the denominator also. Now I'm going to put infinity in both of them. Numerator is also something infinity. Denominator is also something infinity. Right?
But cancel both.
They can cancel. That is true. But now you see, so typically what happens is if it's 1 by infinity, you say it's 0. It's a very small number, right? So now you think about it. This is infinity. And this is e to the power 20 times of infinity. Which number do you think is higher? Is infinity higher or is e to the power 20 infinity higher? Right? So this thing is infinity. This thing is e to the power 20 times infinity.
Then we are applying a L'Hopital rule.
Sort of. Yeah.
So that x playing a L'Hopital rule, it will go for in 0. E power minus infinity is 0. So that term becomes 0.
Yes, exactly. So I am just telling you in a naive way, not the L'Hopital way. So this is infinity and this is a larger infinity. Okay. So it still comes out to be like 1 by infinity sort of a thing, right? Your denominator is very, very large. So when it's very large, the whole term approaches 0.
0, yeah.
Right? So this whole term is going to become 0. Right? So you have, this was 0. This is also going to be 0. So when you putting infinity here, it's all 0. The only time you do it, the next time you do it, you're going to fill 12.5 here, and this one and this one. Um, Try to solve this, like have a calculator handy. I think it should give you the right answer. I have not solved it explicitly myself. Did you get exactly this thing with including this
Yes,
20
yes,
e to the
ma'am.
power
I
250?
am. I have done in this way only. I'm
Okay.
asking. Uh, I am asking. In the end, we are getting one common part, because when we summarize this part in the next question, I think we get it summarized part only in next to this question. uh,
Question number
um,
three,
uh,
four.
Question number four, and I think five. Yes, yes, yes. This one.
Ah,
One minus. Get the summarized formula for this one. No? This
uh-huh.
one minus part, because we get the correct
Okay,
answer
okay,
here.
okay.
This
Okay,
is the
okay.
final. We can summarize this part
Uh-huh.
in this way. So how can we get the one common here?
Okay.
In the whole process of solution, I am not getting this one part only.
Okay, okay. So this one part here, now you see the main difference there is that here there's an x here, and in that one we are filling up the x,
I
right?
have taken the common part also.
Ma'am,
You just
this is a property we are using capital F dash of x equal to small f of x. If you
Uh-huh.
differentiate, we will get small f of x. You have to compare like that. Which differentiation is coming for that f of x? That
That
capital F of x.
that is
Uh,
also true. That is true actually. You're right. So, okay, so what I can do is
uh,
okay, I understand what all the confusion is. I have not explicitly looked into each of the solutions. Like, I have the overall picture, but which step gives you what? And these solutions also don't have each of the steps. So for question number 2, 3, 4, for these integration questions, either I will solve them and give you a full solution, or I'll ask the other TAs, the ones who are setting up the questions, if that can be done. Okay. Um, that's going to help, right? Yeah. Will that be okay?
uh, uh, as of now, okay, ma'am.
Yeah.
But one more question for the
Mm-hmm.
skewness part, ma'am. Please
Okay. Okay. Okay.
scroll
Okay.
down.
Okay. Fine. Just to mention, this third question is also going to be solved on similar
Yes, yes.
lines as the
Because
second one.
one to fifth question are of same
Yeah.
pattern.
Yep. Yep. Yep.
So
Yeah.
uh,
This
and scroll down. First is skewness question, I think.
few
Eighth,
distance.
I think,
Eighth is,
where
was
we
it
get the
skewness in this
skewness.
one?
Yes, yes, yes. Skewness part, coefficient of gamma,
I think it
coefficient
was in
gamma.
the previous section, right? Not in this one. I'm saying it would be assignment
No,
fourth.
no, no. The assignment fifth part is gamma, coefficient of skewness gamma.
Which one is it?
Mm,
I think it would be in assignment four, right?
no, ma'am. It is in
Uh-huh.
assignment five.
Okay.
Scroll down slowly so that I can find it
Okay,
out.
I let me check. Okay, let's go inverse. This one is
No,
RDUNF. This is mean and standard deviation.
no,
This
not
is
this one.
Chebyshev's theorem. This is percentile. This is deciles.
Hmm.
Oh, this one.
No, no.
Kurtosis.
Is
Okay. This one.
yes, ma'am. This one,
Okay.
gamma,
So
gamma
question
one.
number
Yes.
9. So
Hmm.
again, it's you
Because,
have
ma'am, answer is come out of square root. We have the both the value of negative and positive one. and both the values in the given solution we have both positive one and negative one. So
Okay. I see.
that's why
Okay, fine.
how we took the
Okay.
negative
Good,
one.
good point. Okay, so what I'm going to do is, so let's say I'm defining that vector. So the way we're going to do this is, let's say I'm defining a vector x, and so the way we define vectors is we'll have C, and in the bracket, I'm going to add this whole thing. Why did it not get copied? I hope it does get copied. Yeah, fine. So this gets copied. I read this. So now in the environment tab, you can see I have a numeric vector. So you, first of all, let's say what they did here, library moments and skewness of this vector. So I'm going to call the library moments, and I'm going to use the function skewness. I'll write x. So it does give me minus automatically. But let's say, since you asked, how can we see that? So let's say I'm going to plot this also. Okay. And the way I'm going to plot this is, how can I plot this? Let's say I'll make a histogram. It's not the best thing here. Mm, say, this is also not helping. Okay, repeat your question.
Ma'am,
So,
the coefficient of skewness is under root of beta 1.
yes.
That is the third mu to the power
Yes.
square, and in
Divided by,
denominator
huh, perfect.
mu to
Yes,
the
yes.
yes.
Yeah.
So after doing a whole thing, we have to square root of that part. So I have got the answer, this a part and C part, but at the time I got confused that what I should pick up for the positive one or negative one. I should pick up the positive one, but answer is negative one. So I want uh, how come we get the negative value here, because in the lecture also it has been told us that square root take the value of both the positive and the negative one. So
Yes.
here answer is only comes with the negative one.
Okay,
So
fine.
this is my question.
Okay. So two things. So if you remember from, if I can just open that lecture. So this was in week 5, right? Okay. If you remember skewness, right? So,
Yes, sir.
so negative skew indicates this is what your graph looks like, this thing.
Hmm.
And positive skew is this. So we talked about where the tail is,
Yes,
right?
yes.
So this is the value. If it's a negatively skewed graph,
Hmm.
gamma 1 is going to take a negative value. But if it's the same magnitude, if let's say it's a mirror image graph, but
Okay.
if then it's going to take a positive value.
Hmm.
Now, so this one, I don't have a better, like I'm not able to make a better figure now, but this is somewhat following the shape that this is higher here and it's going lower on this side. It's not very evident because these things are probably something like an outlier, because its graphs are never perfect. Okay.
Okay.
But if I can trace it like this, so it's follow, if you can follow my mouse, it's going like this and it's dropping more here. So the tail is on the left, but so which is why the skewness command directly is giving you a negative value. Right? Now, of course, I would like to add here that if you're manually doing it, and if a question similar to this does come up in your exam, then there is no way for you to, without plotting it, there is no way for you to say whether it's going to be positive or negative. Right?
Yes, sir.
So that of course is going to be there. But
Hmm.
the way the question was asked here, like it was stored in a data vector, so the coefficient in this temp variable, this was of the idea that you will solve it through R.
Because
Okay.
at the time of picking up the question, I am sure that the answer can be the positive and negative one. So,
Hmm, hmm, hmm.
but if I choose the positive, it shows the
Yes.
negative one. The answer may be incorrect here. So that
No,
is my
no, yeah,
question.
yeah, yeah. No, but you can see here, right? So when we did
Hmm.
this in R, R is
Hmm.
returning a negative value, and
Okay.
it is also evident from the plot. But
Okay. Answer is
to,
negative here
answer
only.
is negative here, right? So you can see
Okay.
this
Okay.
one.
Okay.
So that's what's happening. Okay, so I think we are running out of time again. This is assignment 5. Most of the questions are on the same lines. Um, okay, I don't know if I can open the. Can you tell me what assignment 3 question 5 was that you wanted to discuss? Is the student here who asked that question? Okay, you have solved the assignment, one of these integration questions, right? Great, thank you. Those of you who are in there, you can just download this figure from the chat, because I don't think I'll be able to upload it separately. I mean, I can, but it'll be just quicker if you download this at the moment. I will
Ma'am,
have
will
this
they
figure.
give, ma'am, will they give our software?
No, no, they will not
Taking
be. You will not have access to our software at the time of exam. So questions like these would most likely not come. You will have
okay, okay.
access to a calculator, an online calculator. In one of the upcoming sessions, we can take a look at that, but it's going to be similar to this TCS calculator,
Oh,
TCS IN calculator, this one.
okay.
So you can just give it a practice so that you're
Can we
comfortable
get the
using it.
previous year question papers, ma'am? This essential data science.
I don't think so. I will ask. Let me ask, but uh, let me ask.
Previous.
I'm actually not sure.
Ma'am, fifth week problem solving session.
Say that
It
again.
gonna be happen again for the week 6 assignment.
Week 6 assignment.
Problem solving session is not happen.
Today, that's week 6, right?
Yes. You have taken the lecture only. That's why
Oh
I'm
yeah, so
asking.
the questions that I
We
no, so the idea was that most of the questions are based on these formulas, right? So again, like you
Okay.
saw, today we did not have any more time. So, and the thing is,
Hmm.
sort of the tie-up that we have, I can only devote 2 hours for this thing. So the idea was that to make the most of it, um, I could only accommodate this much.
Okay.
Although, so I am not exactly in contact with the other two TAs who are taking the sessions on Saturdays and Tuesdays.
Today we have provided the two links for the same
Oh,
timing,
for
6
the
to
same
8.
timing. So I think the Tuesday one is pre-scheduled. It's been preponed. I think the TA has some other work the next Tuesday.
Oh,
Okay. So this might happen because again, we are also been working in our lab, so it can happen sometimes that we might have to prepone, postpone some sessions. So anyway, there will be a session tomorrow, 3 to 5.
okay.
Um,
We
in
can
case
ask
you
the
can
other
attend,
one.
try and attend that if you have time, and in case they do solve some questions, that will be nice. But yeah, it's
Okay.
just I did not prepare these questions because there was already so much to discuss. See, again,
Okay,
we
ma'am.
have
Thanks for the lecture
assignment
part
4.
also.
Yeah. So yeah, so again, we are still left with assignment 4. In case you have some question here, we will discuss it in some other session now. All right. So
Okay.
let me stop sharing my screen then. I think we've just
Ma'am, can you give next class that previous year question papers regarding this course?
I am not exactly involved in the question paper making team. I am only there for the sessions, but I have noted down that you would like to see the previous year's questions. So I'll talk to the TAs who set up these questions, and if they can send you a link or a PDF, that'll be nice. I'll talk
Okay,
to them.
thank you, ma'am.
You can always, anyway, again, so by the way, most of the questions that, so not for today's session, but in other sessions, any of the questions that we are discussing, they are either exactly the previous year's questions of that week or slight modifications of those, because sometimes previous year and this year's questions are exactly the same in your weekly assignments. So we don't discuss those, we discuss slight modifications of those. On the other hand, for the previous year's actual exam, those questions I will ask if they can provide you. Maybe not now, but towards week 10, week 11, once you're done with most of the course.
Okay, thank you.
Yep, that will be good, right? Perfect. All right, so I'll stop sharing my screen then. Thank you so much for attending the session, and I will see you all next week then.
Thank
Yeah?
you.
Okay.
Okay, thank
All
you for
right.
the class.
Good night, everybody. Bye-bye.